Biomimicry, let me tell you a little bit about the field. I started following it in 1990, came out with a book in 97, which looked pretty much at research. Now it's very much more in industry. To give you a sense, in the last 20 years, a survey that was from 1985 to 2005, the patents that have biomimetic or bio-inspired in their title have increased by a factor of 93 against a background of 2.7 time increase in patents. So it's really, there's a ski hill of patents that are starting to come out. If you Google biomimicry and its synonyms, bionics, bio-inspired, you'll get 28 million Google pages. So it really has leapt out of academia, and now it's very much in industry R&D labs. These are, as Sue's mentioned, we have a consulting firm called Biomimicry Guild, and these are some of our clients currently. And what we do is we work with the innovation lab, and they will ask us questions like this. You know, how does nature capture CO2, for instance? And we will look amoeba through zebra at bacteria. How do bacteria capture CO2, fungi, plants, animals, all the way across taxa, to come up with a set of novel and new strategies. They are novel to us, but they're earth tested. And what we found, this is in a year, we did a project called Nature's 100 Best, where we sorted through the biological literature with a list of sustainability challenges on one hand, and the biological literature on the other hand, and we had a team of 10, and found amazing things, some of which have been mimicked already, but many of which should be mimicked. And you can find some of these on asknature.org, which is our site. Novel. Interestingly, there's a guy named Julian Vincent who did a survey of 30 million human patents. And he said, given a certain set of challenges, how have we solved those challenges in the past? And it's a program called TRIZ, T-R-I-Z, that actually did that analysis. He did the same, and it found that there's a certain set of inventive principles that we use over and over again, sort of our bag of tricks. Then he looked at biology and said, given the same set of challenges, what have other organisms, how have they solved their problems? Turns out there's only a 12% overlap, meaning 88% of the time, it's a novel solution. And that's why I think a lot of R&D labs are going for this. It's also, you know, they very much are looking at it as a way to go towards a sustainable solution as well. So let me tell you about some of I'm going to run through these quickly, but I want you to get just a feel of the field. One that I'm very interested in is looking at CO2 with all the talk about how do we geologically sequester CO2. The nagging feeling to me was that really CO2 is not a poison to anybody except for us in the natural world. In fact, it's a building material. And the idea of sequestering large amounts of CO2 beneath the earth is kind of crazy if you think of it as a nutrient or a building material. So for instance, coral use CO2 to build their reefs, which is a very hard, tough ceramic. All the shells that you see in the ocean, CO2 is part of the recipe. So there's actually, some of you may know this, Vinod actually invested in Calera. Brent Constance is a coral reef expert. And he had heard that concrete, actually cement, concrete is 6 to 8% of all CO2 emissions. One of the big problems is cement, which is a raw material for it. It's got to go into a kiln. It's got to be fired. It's very, very energy intensive. He said, wait a minute, coral reefs are doing this all day long. So they are investing now in a technology that'll take CO2. Imagine CO2 coming out of a smokestack in a cement factory and bubble that together with seawater to make concrete in his case. There's other companies like CO2 Solution and Carbozyme that are doing the same thing, and they're using the recipe that mollusks, seashells, use They're creating flue scrubbers that take CO2 and turn it into limestone, which is the raw material for cement. Plants take CO2 and turn it into long-chain polymers called starches and sugars. Plastics are basically long-chain polymers with carbon at the backbone. A guy named Jeff Coates of Novomer studied this and came up with a catalyst that is able to overcome CO2's reticence to hook up. That's why you have CO2 in fire extinguishers, because it's really hard to get it to react. But he found a catalyst that's able to make biodegradable plastics out of CO2. The other material he uses is lemon juice, like a limonene, waste product from citrus. So thinking about CO2 as an organism would, that may change our equation. Energy. There's all kinds of things going on in bio-inspired energy devices. This is an interesting one. There was this research that came out. This is a company called Vivace. Research came out that said trout can't possibly swim upstream. They're not using enough energy. What are they doing? And no one could figure it out until they slowed it down and they realized that the trout make these hydrodynamic sails of their bodies. And they literally will head towards turbulence. They'll head towards a vortex and they'll surf it. They'll grab it and they'll allow it to sling them upstream. And they go from vortex to vortex. Even the vortexes created by other fish, they'll surf. And this is using that idea to capture what's called vortex-induced vibrations, which used to be a problem in oil and gas platforms in the ocean. They always try to fight those vibrations, and instead somebody has tried to figure out how to capture the energy of those vibrations. We heard a lot about thin film solar cells. There is a category of thin film solar cells called dye-sensitized solar cells that are based on photosynthesis. Actually, the dye, chlorophyll. They're not as efficient as PV, but they're really good at in vertical applications and from dawn to dusk and in very high heats. Whale Power is an interesting company. Believe it or not, there's a scientist who studies humpback whales, and his name is Frank E. Fish. I sort of collect these nominative determinisms. There's another one in this presentation. See if you can find it. But anyway, he studied the flippers of the humpback whale, and there's these tubercles, these scalloped edges on the leading edge. And it turns out that plays with water in such a way that it's really an incredible drag reducer. In fact, when he put it on airplane wing model in wind tunnel tests, found a 32% reduction in drag and a 6% increase in lift, which is a lot in aeronautic engineering. 32% increase decrease in drag. I think I said increase. That's a lot. The lift is interesting because it allows wind turbines to go at slower speeds. This is an Australian company called Biopower that is looking at harvesting wave energy, and it's using the kelp as a model. And the claim to fame there is both the anchors that you see that are like the holdfasts of the kelp, but also the fact that in a storm surge, the device literally goes flat onto the ground to avoid rather than try to buttress itself against storm surge.